Our standard story of the universe follows a very specific clock. It starts with the Big Bang, followed by a slow, gradual assembly of stars and galaxies over billions of years. The James Webb Space Telescope was built to look further back into that clock than ever before. Instead of finding the faint, messy clumps of gas Webb expected, it captured massive, multi-armed spiral galaxies sitting right at the dawn of the timeline. These ancient galaxies exist where the math says they cannot. Their presence breaks our standard models of how and when the universe evolved. This timeline error is part of a broader structural collapse. Even in local spiral galaxies, the stars at the outer edges spin at velocities that defy the gravity of their visible mass. To bridge the gap between that math and reality, science introduced dark matter, invisible, unverified particles that we assume are holding everything together. We added a second patch, dark energy, to explain why the universe's expansion is accelerating. The standard model now rests on these two invisible placeholders. When reality forces us to rely on invisible, unmeasurable forces to save a theory, the error lies in the geometry of the model. The Integrated Toroidal-Syntropic Model, or ITSM, proposes a mathematical fix that removes these invisible particles entirely. It starts by mapping the cosmos away from a flat, closed box into a multidimensional torus. This shape functions as an open thermodynamic circuit. It constantly takes in ordered information, a process called Syntropy, reversing the usual path toward decay. This chart shows recent DESI survey measurements of cosmic expansion. The black data points track perfectly with the solid blue ITSM curve, because this toroidal geometry naturally drives expansion without needing dark energy. This open circuit allows the universe to function as a continuous, self-sustaining thermodynamic engine. This macro shape changes the very texture of space. It treats the vacuum as an active liquid medium, the superfluid plenum. Imagine a boat moving through water. Normal matter, like a star or a galaxy, interacts with space much like an object moving through a fluid. In this simulation, notice the red-dashed yield boundary. Below this threshold, mass locks to the fluid's inherent spin, generating a massive acoustic wake. Within the torus, this wake creates a rigid geometric drag, a fixed 2/3 interaction mapped by these 3D topographical spikes. What astronomers have identified as halos of dark matter is actually the hydrodynamic drag of a galaxy shearing through the superfluid vacuum. We can test this fluid math against the SPA-RC database, which contains the rotation profiles of 175 spiral galaxies. For the galaxy NGC 5055, the thick red line represents the ITSM prediction. It threads through the black data points using only geometric constants, without any manual tuning. Dark matter models require scientists to manually tweak the interaction parameters for every galaxy they study to make the results match. ITSM maintains global consistency. Across the entire 175 galaxy sample, the results cluster tightly around the local distance ladder benchmark, using the same geometric anchor for all of them. Mapping hundreds of galaxies with zero free parameters suggests we are looking at a fundamental physical law. A scientific theory must prove itself by predicting data we haven't seen yet. The ITSM framework has established hard mathematical predictions for upcoming JWST surveys and pulsar timing data. Any deviation from these limits will prove the model wrong. This brings us back to those ancient, mature galaxies that broke the standard timeline. In this new framework, those galaxies are a predictable and natural outcome of a fluid cosmos.